Hello everyone, very warm welcome all of you. In this session, I'm going to discuss you basic thermodynamics questions of GATE 22. So let's start doing all this problem, my dear. Very easy problem of heat engine. So which one of the following combinations are allowed? In this problem it is asked. So let's start doing this. So what is the problem, guys? A heat engine extract QH from thermal reservoir at a temperature this and reject QL to a thermal reservoir this while producing work W. Which one of the following combination is correct? Very easy, guys. Suppose there are two reservoirs. This is the reservoir 1. This is your heat engine, and this is your reservoir 2. Clear? Heat is coming, heat is going, and this is your QH. Higher temperature it is coming. This is your QL and this is your W. It is coming from 1000 Kelvin and it is coming from 100 Kelvin. Okay. Now guys, option number 1, QH is your 2000 and this is your 500. So first law of thermodynamics, if you check, guys, QH minus QL. First, if you apply plot, then QH energy in is equals to energy out, W plus QL. So this is the violation. Option number A is the violation. Therefore, it is wrong because QH is your 2000 and it is going to be your 500, means 1000 plus 500. That is the violation. Right? Therefore, it is wrong. Next option you check, QH is your 2000 and 750, 1250 plus. So it may be correct, but this is also, it may also correct, but this may wrong. Right? So these two options are wrong. Now we have to apply the Clausius inequality also in this. So now if you apply the Clausius inequality, guys, so by first law of thermodynamics we have checked there whatever amount of energy that is going to in, same amount of energy is going to out. So there's a violation in the option number A and option number D. Okay. So now let's move to the Clausius inequality. So Clausius inequality, you know very well, for a reversible heat engine, right? Del Q by T should be less than equal to 0, right? So for a heat engine, del Q by T less than equal to 0, del Q by T less than equal to 0. Okay, now guys see. Now if we apply the Clausius inequality in the case 1, in the option number B, that 200 joule divided by Q entering at temperature 1000, okay, minus Q leaving, QL leaving is your 750 divided by 1000 divided by 100. It is going to be your 2 minus 7.5. This is your minus 5.5, which is less than 0. That is correct. Less than 0, which means it is correct. Only one option will be correct. Therefore, option number B is correct. Clear, my dear? Because when you apply the Clausius inequality in this part, there will be violation. It will be greater than 0. If you apply similarly, it will be greater than 0. Therefore, the right answer is option number B. Okay, so use first law and Clausius inequality, you will get the right answer. Next question. Very easy, guys. See? Which of the following is false? Which one of the following is false? It is asked in this. See, my dear. Which of the following is false? For ideal gas, enthalpy is independent of pressure. It is absolutely right. Ideal gas, it depends on enthalpy is equals to H is equals to CPT. It is independent. Next question. For a real gas going through adiabatic reversible process, the process equation is given PV to the power gamma constant. P is the pressure, gamma is the ratio. So guys, it is PV to the power gamma constant is valid only for the reversible, only for ideal gas. Only for ideal gas going to the reversible adiabatic process. Reversible adiabatic process. Remember that. Clear. Therefore, as per the question, the right answer will be this option number B. Why? Because it is applicable. It is not applicable for the real gas. What is written here? Real gas. This is the wrong line. Therefore, that is correct answer. Option number B is correct. Next question. See, my dear, very easy question. Consider a fully adiabatic piston cylinder arrangement. Fully adiabatic piston cylinder arrangement. This is the piston position S1 and S2. Atmospheric pressure is this. This is the initial position. There is the expansion of the piston. Initial length is L1. Final length is L2. The piston is massless. Area is A. The fluid inside the cylinder ratio is gamma. Okay. The piston is initially located at L2. The inside pressure of the air inside the cylinder P1 is greater than P0. So whenever P1 is greater than P0, then there will be expansion, right? Inside pressure is more than the outside pressure. If S1, the stopper, okay, the stopper S1 is instantly removed. This is a very important line. The stopper S1 instantly removed and piston moves to the position S1, okay? And where the equilibrium pressure P2 is greater than P0. What is the work done by the piston on the atmosphere during this process? So guys, it is very easy. We know work done on the atmosphere. In this, always remember, we have to consider the atmospheric pressure and change in volume. Right, atmospheric pressure and change in volume. So we know P0 and V2, we can easily write, guys. V2 is nothing but L2 into area is same minus this is L1, area is same. So this is going to be your P0A L2 minus L. So always remember, while calculating the work done on the atmosphere, we consider the atmospheric pressure because the expansion against the atmospheric pressure that we have to call. So expansion against the atmospheric pressure is the change in volume against the atmospheric pressure. P0 A L2 minus L1. The right answer is B. B is the right answer. Clear? Next problem is ideal gas question. Very easy. Very easy, guys. Try all of you. Consider the mixture of two ideal gas X and Y with molar mass. Molar mass is given 10 kg per mole, My 20 kg per mole in the container. The total pressure is PT. Total pressure is given 100 kPa. Total volume is 10 meter cube and the temperature is teens of Kelvin. The mass of gas X in the container is 2 kg. The mass of gas Y in the container is. So mass of gas Y is asked. Guys, very simple question. We can use this. First of all, we are going to apply the ideal gas equation. Ideal gas equation, we know PV is equals to N number of moles and universal gas constant R2. So pressure we have total pressure 100 kPa, right? Kilo, and volume is your 10. Number of moles we can find out. R is 8.314 kilo, right? And temperature is your 300. Once you solve, you are going to get N number of moles. Let me solve this, guys. 100 into 10, PV is equals to nRT, universal gas constant. Okay. 8.314 kilojoule, kilo per mole Kelvin. Right. So this we are going to get 0.4. So once we got the total number of moles, we know very well that total number of moles is nothing but summation of moles of X and summation of moles of Y. It is going to be your 0.4. Number of moles is mass by molecular mass. So molecular mass for X is the mass of X is 2 kg. So 2 by 10. That is the mass number of moles of, and here its mass is My. upon the molecular mass is 20. Once you solve, this is 0.2 means my by 20. My by 20 is equals to 0.2. So this my you are going to get 4 kg, right? This is the right answer, 4 kg. Absolutely right answer, very easy problem. So this is the way we can calculate this. Okay, thank you. So now the question is over. Thank you everyone. Thank you for joining me. Thanks a lot.